Okay, welcome everybody to our Monday afternoon seminar. Our speaker today is Robert Reischke from the University of Bochum, and he will tell us about fast radio bursts and tests of the equivalence principle. So Robert, please, you have the virtual floor.
Thank you. Yeah, thanks for having me during these times. I want to talk about fast radio bursts and how to test the equivalence principle, and also some other recent stuff I did together with two friends, which are Steffen Hagstotz from the Oskar Klein Center in Stockholm and Robert Lilov from the Technion in Israel. And so this talk is basically based on the two papers listed here. So if you want, check them out. And I will tell you the menu now for today. So what is the plan? So first I want to give a short introduction to fast radio bursts. And then I will move on to tell you about how equivalence principle tests with fast radio bursts worked in the past and what the problem with this is. And I will then move on to show you how you should do it and talk about dispersion measure correlation. So I will also explain what the dispersion measure is. At the very end, I will also talk a bit about fast radio bursts and how you can measure the Hubble constant with fast radio bursts, which is a recent paper we loaded up on the archive. So let's start. What are fast radio bursts? So everything you need to know is basically in the name. So they are very short transients in the radio regime, and they are quite bright. So you can see them in a large distance. So one problem with those things is that the mechanism which causes them is still, well, unknown or debated. It might be magnetars. There were a few papers quite recently, and they have been first discovered 2007. So they're quite recent events, and they usually last only a few milliseconds and are, as I said, quite bright. And the frequency range is between 300 megahertz and 8 gigahertz. When they were first discovered, it wasn't really clear whether they are extragalactic or not, but since the discovery, there have been many events where it's clear that they're extragalactic, but there also have been events which are in our own galaxy. And at the moment, we know roughly 100 events, but this should increase very much in the future because there will be dedicated searches for fast radio bursts. Another interesting thing is that some radio bursts also seem to be repeating. So it's not just a single burst, but they repeat on a certain time scale, which could hint at the mechanism. But as I said, this is still very much under debate. And debating the mechanism, there's actually an interesting webpage and an accompanying paper for that shows or lists all the possible mechanisms. So if you go to FRBtheorycat.org, you will see a list of all mechanisms and whether they have been ruled out or whether they are still in the game. So that's, I think, quite handy in the fast radio burst community. So so there are very many things proposed. So for example, neutron stars or mergers or AGN. So there is a long list, but as I said recently, at the end of last year, there was a paper from the CHIME collaboration, which observed a bright millisecond duration radio burst from a galactic magnetar. And so at the moment, everything seems to be turning a bit in the direction of magnetars, but the situation is still debated. So how are FRBs distributed in the sky? So if you look at this map, you have the Milky Way here. And what you see is they are not correlated with the Milky Way. So which already tells you that, well, they are probably extragalactic. And so the larger the dot in this picture is, the further away is the corresponding fast radio burst. I will talk a bit this more later, how this actually works. So as I already said, the detection so far was mostly incidental, right? You see it, and then yeah, you put it in the catalog, but there was no dedicated searches going on. But we expect in principle rate. So this is not the rate at which you observe, but it's the rate of events you expect is roughly of the order of 10 to the 3 to 10 to the minus 4 per night. So you should be able to see in principle quite a lot if you do dedicated searches for these events. So what is interesting about the FRB, or how do they actually work? So you have a radio signal, just here shown on the left. And this radio signal, when it's traveling through the ionized mediums, through the extragalactic medium, it gets basically dispersed due to constant scattering, and due to constant scattering. And what's happening is that you expect a pulse delay of delta t, which goes with the power law of the frequency to the -2. And this is what you see here in this plot, where you see the frequency plotted against the delay, basically, or the arrival time. And you have this typical power law here, and this is basically what you measure. And the proportionality constant depends on the integrated electron density along the line of sight. So the Coulomb density, if you integrate it from the source to the observer. And this is what is called the dispersion measure. And it's usually abbreviated with dm, which should not be confused with dark matter. And what you see here is that you have this additional factor of 1 plus z, which basically comes from the rest frame redshift of the whole thing.
Sorry, Robert, Pierre has a question. Can he ask you now?
Yeah, sure.
Pierre, please.
Yeah, so here you're writing the dispersion measure as its theoretical expression related to what is its cause, so the density of electrons.
Yes.
But how is it defined from the observational point of view? Like, say you've got the burst, how do you get that number that is called the dispersion measure?
Okay, basically you fit for this power law of the frequency dependence. So you take this plot on the left and you look for the proportionality constant in this power law up to some constants, which you don't so numerical constants which you don't care about, but you basically fit this power law to extract the dispersion measure.
So if the power, sorry, I missed something. If the power law here, I mean, if the delay goes like the frequency to the -2, is that the power law you're talking about, or is it something else?
No, this is what I mean with the power law. Yes. So
it's not exactly -2. It's -2 plus or minus something, and we need to measure that. It's just I just don't get how this dm is defined exactly.
Okay, so no, so you know, so what you know is that it falls off with nu to the -2. That you know, that is fixed. But what you don't know by how much actually. So the constant in front, this is what you fit for. This is the dispersion measure.
Okay, thanks. Now it's much clearer. Thanks.
Okay, sure. Okay. Right, let's move on. So if you look at the dispersion measure itself, you can split it up in different contributions. So you have one contribution which comes from the host, which is the host contribution, which is just the galaxy or the environment the FRB is sitting in, and there it already picks up a certain dispersion measure, right? Because it sees a certain amount of ionized stuff, and it depends where it sits in the galaxy, basically, right? So if it's sitting at the end of the galaxy and then the radio burst has to travel through the whole galaxy, it will be larger. And this is one of the main uncertainties in the whole business. So then you have a contribution from the large-scale structure, from the free electrons basically in the large-scale structure itself, and you have a contribution from the Milky Way. And the contribution from the Milky Way can be modeled quite well. And for example, you can check this with pulsars quite accurately. And what for cosmology purposes is most interesting is the dispersion measure, which originates from the large-scale structure actually. And if the fast radio burst is at sufficiently high redshift, this is also usually the dominating contribution. So yeah, so one important thing is that the redshift scaling of these contributions is actually different, or slightly different, because this is also how you can tell them apart in the end, right? So the large-scale structure contribution basically scales with 1 plus z over the expansion function, and the dark matter host contribution scales with 1 over 1 plus z, whereas the Milky Way contribution is constant. So there are different redshift scalings in the game. So therefore you can, in principle, if you have a lot of FRBs, you can distinguish these different contributions. That is the basic idea. So let's focus on the large-scale structure contribution. So as I said, it's a line of sight integrated electron density. So let's rewrite the electron density a bit. So what do you have here is, first of all, you have the ionization history, which is called FRZ, so which tells you how ionized the large-scale structure basically is. You have a background contribution, which is the 1 in the brackets, and you have possibly perturbations, which is the overdensity, so how perturbed the background is, and the electron bias, because you need to convert the matter density to an electron density, and this might be biased with respect to the matter density, because, for example, you can imagine that you have feedback which blows electrons out of galaxies and so on, so you will have some bias there. Okay, and then you integrate the stuff over some distance measure, and this gives you basically the large-scale structure contribution. So you also have the baryon fraction, of course, because this effectively gives you the number of electrons, and yeah, you divide this by the mass of the protons. So the important part is that depending what you do, you always need the redshift of your sources, basically, or some redshift estimate. And this will become important a bit later as well. So if you want to know all about the fast radio bursts, which have known redshift information, which are only very few, as you will see later, there's an interesting paper which also used these fast radio bursts, where you have the dispersion measure, and you have also an independent redshift estimate, because you did a follow-up of the fast radio burst. And there's a paper in Nature from last year, which measured basically the baryon fraction in the universe using these fast radio bursts, and claim to have solved the missing baryon problem. Okay, so now, since you know what FRBs roughly are, let's move on to equivalence principle tests with fast radio bursts. So how are they done? So the basic idea is that if the equivalence principle holds, then all photons move just on null geodesics, and all photons, irrespective of their frequency, move basically on the same path. As soon as you break the equivalence principle, this doesn't have to be necessarily the case. And what will happen is that the time delay you are measuring picks up an additional delay, which is additional to the mu to the -2 scaling, which we talked before when talking about the dispersion measure. And I call this a dietetic graph here. And what has usually been done is that one assumes for this gravitational time delay, one would assume the normal classical Shapiro delay expression, which would just be this expression over here, where you integrate over the potential along the line of sight from the emission to the observer. And what has been done usually is that you have the idea, okay, let's assume we, for example, only know a subset of the potentials along the line of sight. And for example, one could look at an FRB which is far away, and then the FRB travels, or the light travels through the large scale structure or through the universe. You say, I don't care about this, and I just care about the gravitational potential of the Milky Way. And I measure the additional time delay, or I put constraints on the additional gravitational time delay due to the breaking of the equivalence principle just from the Milky Way. And by this, I would put an upper limit on the deviation from or from the equivalence principle. So the deviation from the equivalence principle would be parameterized here by this parameter gamma, and this would be 0, for example, if the equivalence principle holds, and would be different from 0 if it doesn't. So that is the very basic idea, but this idea has a very fundamental problem. So the equation I just showed you assumes, of course, is basically a Newtonian limit, and assumes that you have the correct boundary condition. It assumes that the potential falls off to 0 at infinity, so that you have, for example, like the Schwarzschild boundary conditions. And this is a problem for these for a cosmological setting, of course, right? Because cosmology is homogeneous. You don't have these boundary conditions, and therefore you could imagine that if you just keep adding structure, then this limit always, I mean, it gets better and gets better, and actually if you consider all the structure in the universe, or just the homogeneous background of the universe, the delta T graph, so this expression here, T graph, this would diverge. So just by considering the homogeneous universe, everything should diverge, and therefore the limit on delta gamma would just be arbitrarily large, or arbitrarily good, if you want. So that is the big issue, that you don't have the correct boundary conditions. So what you should rather use is, you should not work with the absolute potential, but in a cosmological setting, you should work with the perturbed potential, or the perturbations of the potential, which I call phi in this case. And then you would just measure the delay from this phi. But the problem now is, if you take an individual fast radio burst, then since phi fluctuates, the contributions to this time delay can be positive or negative. So you can't set any upper bound with individual fast radio bursts. So that is the basic problem, and there's a lot of literature where this has been done, that they took individual fast radio bursts and went down this route of just considering some known structures along the line of sight from which they can reconstruct the potential, and by this put an upper limit on this delta gamma parameter, or on the deviation from the equivalence principle. However, this cannot work because of the reasoning I just explained, because the contribution basically fluctuates. And the equation I write down here is the only basically consistent equation you can write down in a cosmological setting, where you don't have an isolated galaxy or so.
Rob, can I ask you another question about this problem? So it seems to me this is a very interesting discussion, right? It's about how should you deal with the effect of the homogeneous universe, basically, on this dispersion measure, on the time delay. And so it seems here that, given, I mean, the equation that you give tells us that the average universe, the FLRW background that we have, does not have any impact on this this time delay if there is a violation of the equivalence principle.
Exactly. Yes.
I suppose that this comes out of the calculation that, I mean, of a straightforward calculation. But do you understand what's going on? How is it that the homogeneous universe, let's say the curvature, the mean curvature of the space-time that is experienced by those photons, how is it that they don't feel this? How is it that we don't have a contribution of the homogeneous universe to that
Okay, I think the problem there is that so that's kind of a null hypothesis test, because I mean if you have the FLRW background, then you still have I mean you kind of assume general relativity or certain things which hold for general relativity, right? But so I think you could have for individual photons or for individual FRBs, you would of course see a gravitational time delay, right? Because you just sample one line of sight and that's it.
Yes. Okay. So the whole point is that with only one line of sight, you wouldn't make the difference. But still, wait. So are we? If we compare the following two situations, so we are in a homogeneous universe, so we forget about the perturbations. Homogeneous universe, we have, and we consider two different situations. One in which the equivalence principle holds, and another one in which the equivalence principle is violated. We take the same FRB. Will they have the same dispersion or not? Would they?
So they would, but just because of the reason that they wouldn't experience a Shapiro delay in the first place because it's homogeneous.
I have to think about that. It's not obvious to me. But yeah, okay, well, sorry, go ahead. It's an interesting discussion.
Yeah. Okay, so we've settled that you can't use individual FRBs. So what to do instead? So this brings me basically to the next point, which is dispersion measure correlations. And how does that work? So that works very similar to what one usually does in cosmology, that you look at statistical properties of certain tracers of the large-scale structure. So as I said before, the redshifts are in general not known precisely. So what we do is we consider angular clustering. So what we basically do is we correlate the spherical harmonical modes of our field and calculate a two-point function or power spectrum or angular power spectrum in harmonic space. And first of all, you could of course just correlate the FRBs, but as I told you before, there are not very many FRBs. So this is just like a bad galaxy survey. So it's not very interesting because FRBs usually are in galaxies. So you would just probe the position of galaxies. So this is not very helpful. Instead, what you would like to do is you would like to correlate the dispersion measure. And the interesting part when you calculate the two-point function of the dispersion measure is that, so first of all, what do you trace? You trace the fluctuations in the electron density, which I label here PEE, which is the power spectrum of electrons, which again, by the bias, can be related to the power spectrum of matter fluctuations. Also, you have a short noise term there, which comes from the mean number of FRBs and from the host contribution, or basically from the fluctuation in the host contribution, how broad the distribution of the contribution from the host is. And this basically introduces a short noise. And the interesting part here is that in contrast to, for example, weak gravitational lensing, or also even galaxy clustering, is that the signal part usually dominates the noise part, even for single sources. So this thing here is usually signal dominated, even if n bar is very small. So therefore, well, let's call it super weak lensing. Problem is, or the biggest issue is that this is still sparse, right? You only have very, very few sources. So you need to be very careful with modeling it and also with the measurement in the end. But this is the basic idea, that you just measure correlations in the dispersion measure itself. So at the moment, this can't really be done because there are only roughly 100 FRBs known, but in the future, this might be very, very feasible. So This correlation of dispersion measures was investigated in a few papers, and it's especially very interesting on large angular scales. So the problem, since it is still sparse, at small angular scales, you will still be shot noise dominated, right? But on large angular scales, you can dig out some signal, and especially since FRBs have been observed at quite high redshifts, you also probe a very large volume with these things if you consider large scales. So I've compiled here a small list of papers. So this was basically first introduced in 2015, and then it was also discussed whether you can use cross correlation with actually a galaxy survey to improve the redshift information of the known FRBs. And then yeah, there is the paper I'm talking now about, and also you could try to figure out something about primordial non-Gaussianities with fast radio bursts. Okay, so let's go back to the equivalence principle. So as I said, the true observable is actually the time delay between two frequencies. And this, again, is the contribution from the normal dispersion measure, which corresponds to the (2⁻²), and the delta t graph, which is the Shapiro delay, which is induced at two different frequencies now, only if the equivalence principle is broken. Otherwise, it isn't. And only if, well, as we just discussed, you have some fluctuating potential along the line of sight, which is not homogeneous. And this would then basically imprint additional correlations in the not dark matter, in the dispersion measure signal. So that is the very basic idea, that you get this additional contribution. And you can now look at how well could you constrain this. So this plot basically is a Fisher forecast, and it shows on the y-axis how well you can constrain this delta gamma parameter. So watch out that this is in units of 10 to the minus 15. And on the x-axis, you see the signal to noise of the experiment, basically. So it's irrespective of the geometry of the experiment, but just by how much signal to noise you measure it. And to put this a bit into perspective, so current constraints on this delta gamma parameter are of the order of 10 to the minus 13-ish. And what you see here is, as soon as you would detect would be able to detect any correlations in the dispersion measure or of FRBs itself, then you would be able to pin down this equivalence principle breaking parameter very, very precisely. And the reason for that is that even though the individual contribution might be very small, since the signal travels through so much large-scale structure and over such a long time, the Shapiro delay is enormous, and any deviation from the equivalence principle would completely dominate the usual dispersion measure from the (2⁻² scaling. Okay, so much about the equivalence principle. This, again, so just to review, this is the basic idea. You just consider angular correlations of the dispersion measure, and by this you get rid of this problem that you only probe individual line of sights, but you probe no correlation, and therefore you can actually use this the equation or the appropriate equation and put upper bounds on this equivalence breaking parameter, which you couldn't do with individual FRBs, which only basically test the background, if you want.
Sorry, Robert, there is a question by Juan.
Yes.
Hi, Robert. Sorry, before we go into the Hubble parameter, which I think it's the hot part of the seminar, I'd like to ask you about another quantity, which is also an integral along the line of sight of the electron density, and that's the rotation measure. So here you're talking about the dispersion measure. So that's how the energy of the photon changes as it travels through the medium. Now there's also the plane of polarization of the photon, right? So if you know a source that has a very clear plane of polarization, for instance, a quasar along the axis of the quasar, and you could follow how that plane of polarization rotates. Of course, you need not just the integral of the electron density, you have to know what's the magnetic field along the line of sight also. So it's a whole integral, both any and b on the line of sight. But could you look for correlations between the rotation measure and the dispersion measure along certain lines? And for those places where you know, well, at least you could infer the magnetic field, deduce whether that correlation gives you more information about the number density of electrons along the line of sight?
Yeah, we are actually thinking about something along these lines at the moment. Whether you can do this, well, no.
It could break some degeneracies, right?
But yeah, you would actually do that. Yes.
So some of the systematics that you were referring to would be somehow, well, as long as you knew the magnetic field along those sides. So you had good measurements of the magnetic field through the change in the angle of polarization. They both go like lambda squared, right? So it's something that helps in terms of the spectroscopic follow-ups.
That's a very good point. Yeah.
Sorry, how could you possibly measure this rotation? You have no idea what's the original.
No, that's incorrect. You do know, because most of the jets in active galactic nuclei move along an axis, and this induces the planar polarization of the light, synchrotron light, which is emitted from that, and that planar polarization is orthogonal to the axis.
So you need to measure the precision of I mean, in terms of the angle. Is that really realistic?
Yeah. It's been measured. That is used systematically to measure magnetic fields along the line of sight.
Okay.
It's a well-known measure. The question is whether you can use that measure. Of course, we don't have 100, like in the case of fast radio bursts. We have millions of quasars, right? Some of them are too far away to make this integral anything, useful for us. But for those quasars that are sufficiently near us that you could do the cross correlation between the fast radio burst and the quasar in the background, you could use that as a cross check. And looking for cross correlations between the two, you break degeneracies. Well, this is something which I've been thinking for some time. I don't know that you were also exploring it.
If you do that, mind the effect of lensing also, that may change also the relative orientation of the jet with the polarization.
It's a good point. Yes, I would argue that that's second order, but that's okay. It could be that there is an effect from lensing on both the planar polarization and sorry?
Whenever you have shear, you would
sure.
If shear is not aligned with it, you will have that problem.
Right, but most of these magnetic fields are very homogeneous on scales of clusters or superclusters, which is where most of the integral goes through. The rest is just fluctuating magnetic fields, whose contribution is zero. Okay, sorry. I just want to know whether you were aware of that.
A brief question, Juan and Robert. Is it clear that always the jet is orthogonal to? Like you were saying, you can always correlate them when the jet is orthogonal. Is it clear that it's always orthogonal?
The plane of polarization of synchronous radiation coming from a very collimated jet, yes, we know how the plane is.
Okay.
The jet. Now, the jet may not necessarily be orthogonal to the AGN, but most of the cases you have an accretion disk, which is very collimating through magnetic fields, the jet. And therefore, yes, they are orthogonal to the disks. But I was talking about the plane of polarization of the light coming from the jet.
Okay.
Particles being accelerated through the magnetic field along the axis and emitting synchronous radiation, which produces a radio emission.
Okay.
With the plane of polarization. Yep.
Okay, so let's switch gears from the perturbations again to the background. So yeah, fast radio bursts and the Hubble parameter. So probably all know the Hubble constant and the long-standing issue, which from local measurements of the Hubble constant and global measurements or early and late time measurements. So yeah, the Hubble constant basically tells you the expansion rate of the universe, and usually you measure it with a distance redshift relation. And here on the right, you see basically the most very up-to-date version of the distance measurement, and you need also an independent redshift estimate. if you want to have a distance scale which you can actually use to measure the Hubble constant. So what kind of distance scale do FRBs basically provide? And as I said at the beginning, you have basically in the dispersion measure, you have a distance measure inside the expression. And if you write down the contribution from the large scale structure as a function of redshift a bit differently, it looks like this. So you have the baryon density, you have H naught there. And you again have the fraction of the of ionization of the IgM, and you have an integral over the Hubble function and some factors of 1 plus z. And so if you measure the slope basically of this relation, this gives you the Hubble constant. So the main problem is that at the background level, this is of course completely degenerate with the baryon density. So you need some prior, for example, from Big Bang nucleosynthesis or from CMB on the baryon density. An additional caveat there is that CMB or Big Bang nucleosynthesis provide you priors on the physical density, and therefore this is rather sensitive then to omega b times h squared, which is the physical density of baryons, rather than just this omega b here. So you would have to replace that if you consider prior from cosmic microwave background or Big Bang nucleosynthesis. So, but this is the basic idea. So I show you again the map of the fast radio bursts here. So here you have your 118 events which are known, and the green dots are now the ones which have an associated redshift with them. And again, the main challenge when you want to know the redshift as well is that you need to do a follow-up, and you need to know where the FRB basically comes from, and therefore you need to have very, very good angular resolution in order to resolve actually the galaxy where the FRB originated from. And that's why there are so far only so few. But yeah, we thought whether you could use these 9 FRBs already to put, well, proof of concept, to put some constraints on the Hubble parameter. So again, here I show you the number of FRBs in a histogram basically as a function of the dispersion measure on the x-axis and the corresponding estimated redshift also on the x-axis, but you see it on top. And what you can see is in principle that you can see them to quite large redshifts, and that they are therefore in principle quite powerful probes of the Hubble constant or of the expansion of the universe itself. However, so far the true FRB population is not very well known. But let's see what we can do with those in which we know something. So here's again one plot about the host identification, how it will look like in the future. So with SCAP and in combination with VLT, you will have very good angular resolution, and you will have a dedicated search. And therefore, with these, you will have a lot of FRBs where you can actually identify the host and therefore take an optical follow-up to allow the host identification and therefore also to measure the redshift accurately. And this will basically push these measurements of the Hubble constant or anything else actually, also of the angular clustering, if you want, push this forward quite a bit.
Sorry, Robert, a quick question. So what is the typical error on the redshift? Because I see here in the plot you give a redshift which is like with 6 digits.
Yes. So the redshift error is basically completely negligible compared to anything, compared to the other errors. Yeah.
Okay. Yeah.
Because you really do spectroscopy basically.
Yeah.
Yeah.
Thanks.
Okay, so what I show you here is basically now this dispersion measure on the y-axis and on the x-axis of the redshift. So this is this dispersion measure redshift diagram, which is very similar to the diagram from which you know from supernova, where you have a distance modulus redshift diagram. So important thing is that you measure the dispersion measure or some estimate of the distance independently of the redshift. That is the crucial point here. And it's basically calibrated by subtracting the contribution of the host and the Milky Way dispersion measure. So what you see here is really only the large-scale structure dispersion measure and as a function of redshift. And basically the most important contribution comes, or to the error budget of the thing comes from the, as I said in the very beginning, comes from the host identifier, from the host galaxy, because you don't really know how big the dispersion measure of the host is. So you need to assume something there. And at the moment, the error we assume is roughly 10%. But we also did a forecast where we basically leave this free as a free parameter, the scatter of the host. Yeah. So one additional thing is that we have a gold sample here, which is shown not in gold but in red, and the whole sample, which is basically all the data points, also the three in the in black. And the difference between the gold sample and the full sample is that in the gold sample, you don't have very close by fast radio bursts, which also lie basically in the galactic plane, and therefore pick up a lot of dispersion measure from the Milky Way. That is the main difference between the gold sample and the optional sample. Okay, so what you then can do is you can use a CMB prior, and you can fit for the Hubble constant. What I show here is the posterior distribution of the Hubble parameter for all individual fast radio bursts in these colored lines, and for the gold sample as the dashed black line, and for the whole sample as the solid black line. What you can see is that the difference between the gold sample and the full sample is basically marginal. And the reason for that is that these additional fast radio bursts, which are not in the gold sample, only contribute very, very little to the whole constraints, because they are quite close to the Milky Way, and therefore their error is quite large, and therefore they don't contribute much to the constraint itself on H0, because they don't probe the large-scale structure itself very much, or not the large-scale structure, but the expansion of the universe itself. And as I said, so the biggest uncertainty here comes basically from the host dispersion measure contribution. And what I also show is basically the usual two lines from the cosmic microwave background in blue, and the SHOES collaboration, so supernova, in green, and the discrepancy. And of course, since we only have very, very few FRBs at the moment, you can't tell very much. But this will increase in the future, and I will show you now how competitive they can in principle be. So here on the y-axis, I show you basically the percentage error you can get on H0 as a function of the number of FRBs. And in principle, you see that a few hundred FRBs with host identification can get the accuracy down to the precision down to 1%. The problem then is, of course, that you need to be very, very careful of systematics, which there might be a lot of them, which we don't know yet about. So this needs to have some very thorough further investigation. At the moment, since we are completely statistic dominated, this is not a big problem. So another question you can ask is whether we can relax some assumptions we did here for larger samples. For example, the fixed contribution from the host. And going back to what I showed you in the very beginning, the contributions to the dispersion measure, that if we have a lot of them, since they have a different redshift scaling, you can use basically statistics to tell these, or a lot of FRBs to tell these contributions apart. So how does it look like if we relax some assumptions? So here we basically simultaneously fit the mean contribution from the host and the matter density in the universe together with the Hubble constant. And this is for 500 events. And you can see, for example, that for 500 events, you can simultaneously determine, for example, the contribution of the host and the Hubble parameter itself to quite good accuracy. Okay.
Robert, I didn't get it. Can you re-explain again? Where is the constraint on omega m coming from?
Right. Okay. So the constraint on omega m comes basically from the expansion function. Right?
Oh, okay. So if you have, oh right, so you suppose that you have FRBs with large redshifts, so you're not probing the slope. Oh, okay, of course, yes. Thanks.
Yes, exactly. So if we go back. If we go back to this here, we basically sample from a distribution which looks like kind of this, if you want. So this is how we generate the mock data, basically. So you have FRBs which are at redshift 2 or so, or some number of them at least. Yes. Okay. So yeah, with this I would like to summarize. So what did I tell you today? So the mechanism of FRBs is still unknown. Also, what is unknown is whether there are some systematic effects which might influence the detection of FRBs itself. And that they are, however, a very promising tool for cosmology and beyond in the future. So what I also told you or showed is that you can't use the background contribution to the dispersion measure to constrain the equivalence principle or anything which is remotely related to the Shapiro delay. You can't do that because you can't put upper limits anymore if you do it properly, or if you put upper limits, then you use basically the wrong expression. Then I talked about the dispersion measure correlations and how they influence the constraints on the equivalence principle breaking, and I told you that as soon as they are detected, the dispersion measure correlations, you have very, very tight constraints on the equivalence principle. And then in the second part, in the last part, I talked about measuring the Hubble constant with FRBs, and this can provide an independent, I put an asterisk here because you still need the BBN prior, so it's not an entirely late time measurement, but it also uses some information from early times, but you can measure the Hubble constant also with these things. So at the moment, all FRB studies you want to do with the actual data are basically limited by the low number of FRBs which are currently available. So you can't construct a two-point function at the moment because there are only very, very few. But in the future, there will be many more events coming from Chine, SCAP, Hyrax, or SKA. So this will be very exciting. And yeah, I'd like to thank you for your attention and take more questions now.
Thank you, Robert, for this very nice talk. Okay. So we have ample time for lots of questions. So I see Juan raised your hand. Please.
Hi, Robert. So with respect to the search for the Hubble constant and in general, even the evolution of the universe acceleration. Now, of course, we have very few now. And as you rightly pointed out, soon we will have thousands. Then the question might arise whether there are different kinds of fast radio bursts, like we have different kinds of supernovae, and perhaps there are certain kinds, like type 1a, that are much better. You can calibrate them or at least standardize them. And you can do also something similar for some types of FRBs, maybe they are the repeaters or whatever, for which you might know the actual physics associated with it. If it's a magnetar, okay, at least you know what kind of object. And then you can standardize those and try to use that subsample as a much better probe of the expansion of the universe. Has this been explored?
It hasn't been explored yet because so since the mechanism is still very debated, so and there are so many outs, so this hasn't been discussed yet. No, but I mean it's certainly an interesting point. And you also another point is, for example, if you consider the contribution from the host, which we assume to be basically constant, but this. So, I mean, galaxies at Redshift 2 are certainly not the same galaxies than at Redshift 0, right? So this is another point, right? And this was one point. What I wanted to show here is that, well, okay, even if you are completely agnostic about it, you don't have to care. But if you put this additional information in, this might also be very crucial to know about this. And if you, for example, if you don't, or if you do it wrongly, you might introduce some systematic effects which you are not aware of, right? So that's there are many things to do there.
Right. Another question which came to my mind has to do with this Redshift 2 limit that you mentioned. So of course that depends on what kind of physics is responsible and how intense those events can be, and therefore how far away can you see them. But if you could reach, say, further than 2 redshift, you could see whether they are related to, so they have some redshift dependence that might be related to star formation rate, for instance, that peaks at around Redshift 1, and see whether it decays at higher redshifts, because then you could use that again as another probe for its nature.
Yes. So I think if we go, it's a very good point. I mean, if we look at this histogram, right? So the largest dispersion measure which has been detected is at 2,500, which is, I mean, if you just blindly compute a redshift out of this, above 3, basically, right? Which is quite.
Well, you have to know that its frequency is radio, right? Because you have to convert centimeters and then get what the parsecs are. Yeah. Okay. Yeah, it's redshift 3. Okay. Thanks.
Okay. There is another question by Matteo.
Hi. Thanks for the talk, first of all. And my question is also on the H0 measurement with the FRBs. And I was wondering, you will not have degeneracy as you have for omega B and H0, but if you consider, for example, different kind of dark energy in your expansion history of the universe, do you think that this would significantly impact the results or the constraint that you can get on that?
But I think it would do it in a very similar way than it would do for supernova, for example, right? Because I mean it's basically a very similar probe, right? Just with just here you have the problem that you kind of probe the baryon density directly at the background level already, where you need the prior for. So yeah, I mean, this is something one could then, for example, test if you have more FRBs, right? So at the moment, I think it would just first of all dilute, of course, the constraints, but also you wouldn't be very, very sensitive because most of the FRBs from the gold sample are at redshift way below 1. I mean, the highest redshift is of this gold sample is at 0.7 roughly. So you aren't very sensitive to dark energy there, but this might change in the future, yes.
Because my fear was kind of that when you get the H0 constraint from CMB, for example, this is done assuming lambda CDM and you get some value. So this is something that seems to could be a problem also in here. So one could, in principle, think of having something more general to be more agnostic, let's say.
Yes, that's true. Yeah, you could. I mean, yeah, you could also do. I don't know. I mean, there are different things. These model independent searches for the expansion function. This is something you could do with, I don't know, PCA or whatever you like. Yes. Yeah.
Thanks.
Okay. Any more comments, questions?
Yeah, maybe before Juan.
Yes, please.
The stupidest question of all. How is it that we do that with FRBs and not with GRBs? Is it that the gamma rays, they are completely, I mean, the universe is transparent to the gamma rays and they just don't have such a dispersion? Or is it something else?
That is a good question.
Oh, good. I'm not the only one to be ignorant about that.
Yeah. But yeah, I would think that I would guess that the error you basically get on the corresponding dispersion measure is way larger than for fast radio bursts. Yeah.
May I comment here? I think it has to do with the energy resolution of those gammas compared to the frequency resolution of in radio. In radio, you can have extremely fine resolution.
Is it?
In gammas, you don't.
Okay.
And therefore, well, there might be a dispersion measure, but it's so fluctuating, so much
Very uncertain. Yeah.
that you don't.
I was wondering that, so if I remember my undergrad course on light propagation in plasmas, because this is what we're talking about, right? We're talking about the effect of having free electrons on, and there is this characteristic frequency, right? The plasma frequency. And I think when your frequency is much higher than that, you basically don't see it. You don't, I mean, you don't care. Is it, am I right when I'm saying that? Like maybe gamma rays, they don't care, but I was wondering, so maybe there is also this effect of just instrumental problem, like you don't have the actual resolution to do that you raised, Juan.
Yeah, I'll have to think of it. Maybe there is this plasma frequency, but I don't know out of my head what's the typical energy of that plasma frequency in the interstellar medium. I mean, of course, not in a dense gas. Okay, but I had another question which had to do with the magnetic fields that I asked at the beginning. So if one could measure properly this out of this dispersion measure, the electron density along the line of sight, you could then use this backwards to put a constraint on the magnetic field.
Yes.
So not just to look for cross correlations between the dispersion measure, that you do because you have very few FRBs and you have plenty of quasars, but here it would be different. You would say, okay, now that I have enough of these FRBs, soon we will have plenty, then you could use that to infer along certain lines of sight, what is the magnetic field along those lines?
Yes.
Has that been thought of? Because we know that we have a fundamental problem in cosmology to know the origin of magnetic fields and whether they cover, say, cluster scales, and therefore they would have to be cosmological in origin, or they are only on galactic scales, and they could be dynamo generated. No? So this could help resolve one of the existing issues on the origin of magnetic fields and their cross correlation on large scales.
Yeah, I think that's a very good point. And so I'm not aware of any of papers in this direction in the FRB
people. What they do is they use say active galactic nuclei with very, say, TV energy particles like Neronov and others, and they see how these particles can per-produce electron positrons and then go out. And this puts constraints on the magnetic field in between, because they would have produced this conversion of energy into pairs of electrons and positrons. But that's the only way I know of measuring the intense magnetic fields in the intergalactic medium. This would be a much more efficient one, because you already have the number.
Yeah, this could be very interesting. Yeah,
number density.
Yeah.
Okay, just a thought.
Yeah. Thank you.
Okay, any more questions? Matteo, did you raise your hand again? See, it's up.
No, it's the one of before. Sorry.
Okay. So any more questions, comments? If not, we can thank Robert again. Thank you, Robert, for this very nice talk again. So I can now stop the recording.